I am Dr. Harjinder Singh, Assistant Professor in Chemistry at Multani Malmodi College, Patiala. In this video lecture, we will discuss UV visible spectroscopy. So, to begin with, first of all, let us see what is this word spectroscopy. Now, this word spectroscopy is made from two words, scopy and spectro. Now, this scopy means to study something. So this spectroscopy, it basically deals with the study of interaction of electromagnetic radiations with matter. So when we study the interaction of electromagnetic radiations with matter, that study is called spectroscopy. Now this interaction of electromagnetic radiations with matter gives gives the idea about many properties and the structure of the matter. And use of electromagnetic radiations, different electromagnetic radiations can give idea about the different information about the matter which is under study. So basically, spectroscopy is a study of interaction of electromagnetic radiations with matter. And the major application of this spectroscopy is to find out the structure of unknown compounds. This is used in organic chemistry. Basically, it is used to find out the structure of unknown compounds. For example, if we have any unknown compound whose structure is not known, we can use this spectroscopy to find out its structure. There are many spectroscopic techniques such as NMR spectroscopy, which is a nuclear magnetic resonance spectroscopy, infrared spectroscopy, then we have a UV visible spectroscopy, then we have a Raman spectroscopy, then we have mass spectroscopy, atomic absorption spectroscopy, and there are many more spectroscopic techniques. So here basically what is spectroscopy? Spectroscopy is a study of interaction of electromagnetic radiations with matter. So in order to understand spectroscopic techniques, first of all we have to understand these electromagnetic radiations. Now as their name indicates, they consist of two words, electro and magnetic. So what are these electromagnetic radiations? These are basically waves that are having both electric field and magnetic field component. So these radiations which are having both electric field and magnetic field, they are called electromagnetic radiations. And these electric field component and magnetic field component both are perpendicular to each other. So in the form of diagram like this. So here you can see in red color, this is a electric field component, which is a electric field, and in this blue color, this is a magnetic field. So you can see it has both electric field component, which is moving as a wave up and down, and similarly you have a this magnetic field component, which is also moving as wave, but both these are perpendicular to each other. Now it's very important point to remember, most of times when we study this spectroscopy or any other technique wherever electromagnetic radiations are involved, only electric field component is responsible for its property. So basically we will study only electric field, the interaction of electric field with matter, not magnetic field. So there are very important terms that are involved in the study of these spectroscopic techniques, or it is involved while studying these electromagnetic radiations that must be remembered. The very first term is wavelength. So what is wavelength? Now this is a wave. Now when electromagnetic radiations move in the form of waves, it at one point it moves at a maximum, at the other point it is at the minima. This maximum point is called crest, while this minimum point is called trough, and then it again repeats itself. So it goes to from minimum to maximum, then again minimum, then again maximum. This maximum point is called crest and this minimum point is called trough. Now what is wavelength? The wavelength is a distance between two crest or two troughs. So if these are the two troughs, so this distance between these two troughs is a wavelength. Similarly, this difference between the two crust is also a wavelength when both are same. So what is wavelength? The wavelength is a distance between, it's a distance between two adjacent crust or troughs is called wavelength. And the units of wavelength is, SI units of wavelength is meter, and usually it is represented in like nanometer. Now nanometer is 10 raised to power minus 9 meter, or it may be represented in the form of angstroms, which is 10 raised to power minus 10 meter. And the symbol for the wavelength is lambda. So lambda is a wavelength. Okay, then we have a frequency. Now what is frequency? The frequency of wave can be defined as number of waves that are passed through a point in 1 second. So if you have any point, then number of waves that can pass through this point in a 1 second is called frequency. And this frequency is denoted by symbol nu. And the units of frequency are cycles per second, since it's a number of waves that pass through the point in 1 second. So it can be defined as the cycle per second or hertz. So these are the two commonly used units for the frequency. Now the relation between frequency and the wavelength. Now the frequency is inversely proportional to wavelength. So if you have frequency, that is inversely proportional to wavelength. And if you remove this sign of proportionality, then you have to replace it with some constant, and in this case this constant is c. Here c is a constant and it is a speed of light. Here c is a speed of light, which is a constant. Okay, so in wavelength and frequency, they are inversely proportional with each other. Then the next is wave number, and the wave number is represented by symbol nu, and the wave number is a reciprocal of wavelength. The reciprocal of wavelength is called wave number, and it also can be represented as the number of waves per centimeter. So the reciprocal of wavelength is called wave number, and this significance is, now if you have an area of 1 centimeter, then the number of waves which are present in this 1 centimeter area is called wave number, and it is denoted by symbol nu bar, and its units are centimeter inverse. So as I already told you, this wave number, which is a nu bar, is inversely proportional to wavelength, or is reciprocal, it's the reciprocal of this wavelength. So it is nu bar is equal to 1 over lambda. Now lambda is itself is equals to is inversely proportional to wavelength from the previous slide. Now here this lambda is itself is equal to c upon nu, because nu was c upon lambda. So if you put this value, it become nu over c. So it's a frequency over speed of light. Okay, the most important thing is energy of these electromagnetic radiations, and energy of these electromagnetic radiations is directly proportional to the frequency of these light. So energy is directly proportional to frequency of these electromagnetic radiations. So more frequency means more energy, and this frequency is inversely proportional to wavelength. So that means lesser wavelength, more will be energy. And if you remove this constant, inversely proportionality, and then we have to replace it with some constant, and that constant is h, which is a Planck's constant. So we can write energy is equals to h nu, where nu is a frequency of electromagnetic radiation, h is a Planck's constant. Since nu is equals to c upon lambda, so it can be written as a hc upon lambda. So from here, where hc is a constant, so here from here we can say energy is directly proportional to frequency. So more the frequency, जितनी ज़्यादा frequency होएगी, more will be energy, and it is inversely proportional to the wavelength of light. So lesser wavelength of light, more will be energy. As I already told, here h is a Planck constant, and its value is 6.625 10 raised to the minus 34 joule second, and c is the speed of light, which is 3 into 10 raised to the 8 meter per second. So these were the few important terms that are involved in while study of these electromagnetic radiation. So now next is electromagnetic spectrum. So depending upon the frequency and the wavelength of these electromagnetic radiations, there are a variety of electromagnetic radiations. So the arrangement of these electromagnetic radiations in order of increasing wavelength. So when we arrange these electromagnetic radiations in order of their increasing wavelength or decreasing in order of frequency, that spectrum is formed, which is called electromagnetic spectrum. So what is electromagnetic spectrum? It's the arrangement of all electromagnetic radiations in order of increasing wavelength or decreasing order of frequency, and hence decreasing order of energy is called electromagnetic spectrum. So this arrangement is called electromagnetic spectrum. So what is electromagnetic spectrum? It's the arrangement of all electromagnetic radiations in order of increasing order of their wavelength or decreasing order of their frequency. That arrangement is called electromagnetic spectrum. So in electromagnetic spectrum, this is a complete electromagnetic spectrum. So here you can see that the wavelength of light electromagnetic radiation is increasing to this side and the frequency is decreasing. So we can divide this whole electromagnetic spectrum into the different regions. The region of with maximum wavelength are called long radio waves. So they have a very large wavelength, usually in the order of 1 to 10 raised to power 8 centimeter. So this region that has a very long wavelength is called radio waves. Then you have microwaves, then you have infrared radiations, then you have visible spectrum. Now the visible spectrum lies between normally 400 to 800 nanometer. So this is a range of visible light, 400 to 800 nanometer. And to the left side of this visible spectrum, you have UV radiations. So these UV radiations, they are having more energy as compared to visible light. And this UV radiation, it falls between 200 to 400 nanometer. The wavelength of these UV radiations is in between 200 to 400 nanometer. Then you have X-rays. So these X-rays are having very high energy or short wavelength or very high frequency. And in last you have a gamma rays. So these gamma rays, they are having very high energy. So these different electromagnetic radiations are used in different spectroscopic techniques. Now in UV visible spectroscopy that we will discuss today, we will use only or we will study only the interaction of UV and visible radiations with matter. So we will deal with the radiations in this range from 200 nanometer to 800 nanometer. So the interaction of 200 to 800 nanometer radiations with matter will be called UV visible spectroscopy, where visible region is in between 400 to 800 nanometer and UV region is in between 200 to 400 nanometer. Okay, so let us start with the UV visible spectroscopy. So as I already told you, what's UV visible spectroscopy? In UV visible spectroscopy, we will study the interaction of UV visible light or UV visible radiation. So UV visible radiations that are having wavelength in between 200 to 800 nanometer. 200 to 400 is UV, 400 to 800 is visible. So when we study interaction of electromagnetic radiations of this range with matter, that study is called UV visible spectroscopy. So let us discuss the principle of this UV visible absorption spectroscopy. Okay, when any electromagnetic radiations or any light falls over a substance, there are few things that can occur. So one is this radiations it is falling over the any substance. These radiations, they may get absorbed. These radiations may get absorbed or it may get transmitted. So the radiations which are falling over the any substance, these radiations may get absorbed or these radiations may get absorbed, or these radiations they may get be transmitted. The third possibility is these radiations may get scattered. Now, and this depend upon the molecular structure of the substance and the wavelength of light which is used. Now, in absorption spectroscopy, now UV visible spectroscopy is a kind of absorption spectroscopy. Now, absorption spectroscopy means we will study the light or the electromagnetic radiations which get absorbed. So, it's a kind of absorption spectroscopy. So, in case of this absorption spectroscopy, the main principle, so when this light is absorbed, when this light is absorbed, it affects the energy levels in molecule. So this, when light is absorbed, it affects the energy of molecule. Now there are three main energy levels in a molecule whose energies get affected. These three main energy levels are rotational energy level, vibrational energy level, and electronic energy level. So when electromagnetic radiations falls over any molecule, they affect these three energy levels. Now out of these three energy levels, the electronic energy levels, they have a maximum energy. That means to change these energy levels or to transitions take place between these energy levels, you need a maximum energy. Then you have vibrational energy level, and these rotational energy levels, they are having lowest energy. So maximum energy is for electronic energy level, then you have vibrational energy level, then you have a rotational energy level. So when since UV visible radiations, they have a maximum, they have a very high, they have a high energy, so they affect usually these electronic energy level. So these electronic transitions between these electronic energy levels, they take place in presence of this UV visible radiation. So when this UV visible radiations falls over a molecule, what happens? These electronic energy levels, they changes. The electron from the lower electronic energy level goes to the higher electronic energy level. While for this vibrational energy level change and the rotational energy level change, lower energy is required. So the necessary condition to absorb these electromagnetic radiations is that the energy of the photon of the radiation, that means the energy which of the electromagnetic radiation, it must be equal to the energy difference between the two vibrational, rotational, or the electronic energy states in a molecule. So that means the energy of the energy of photon, or the energy of electromagnetic radiation, it must matches between the two electronic energy levels in case of electronic transitions, or two vibrational energy level in case of vibrational transitions, or two rotational energy level in case of rotational transitions. So this energy of the photon which we are giving, it must matches these two energy levels. Okay, then the record of the amount of radiations which are absorbed or transmitted by a given sample as a function of wavelength is called absorption spectrum. So what's the absorption spectrum? It's basically a graph in which we record the amount of light which is absorbed as a function of wavelength, and the instrument which is used to record spectrum is called spectrometer. So in nutshell, what we can draw from this discussion is, in a molecule there are three main energy levels. One is electronic energy level, other is vibrational energy level, and third one is a rotational energy level. The energy of the electronic energy levels is maximum, then you have vibrational energy level, and the energy of rotational energy levels is minimum. So when the light of this UV visible radiations of this range between 200 to 800 nanometer falls of the substance, it basically affects the electronic energy levels, and the electronic transitions take place and light is get absorbed. But for the absorption, what's the condition? The energy of these electromagnetic radiation must be equal to the energy difference between the two electronic energy states. That means if you have two electronic energy states like this, so and this is an energy gap between these two electronic energy states. So when you give the light from the external source, the energy of this light or the energy of this photon, it must be equals to the energy gap between these two states. So if the energy gap is in between these two states is equal to the energy of these electromagnetic radiations, only then absorbance will take place. Next is presentation of UV visible spectrum. Now the UV visible spectrum is recorded as on the x-axis we take a wavelength of the light which is used, so it is 200 to 800 nanometers, so here it is up to only 300 nanometer, and on the y-axis we take absorbance. So on the x-axis wavelength is used, on y-axis we take the absorbance. So absorbance of the electromagnetic radiations is drawn as a function of wavelength of light. So as we can see, so at the 200 nanometer you can see there is a very little absorbance, then the absorbance starts increasing and it reaches a point where this absorbance of radiations become maximum, and then it starts decreasing and it becomes zero at the certain wavelength. So you get this kind of peak, which is a kind of broad peak. Okay, so you get this peak. Now here there's one term which is used, lambda max. Now what is this lambda max? This is a wavelength at which absorption become maximum. The wavelength at which absorption become maximum is called lambda max. For example, here the absorption is lower, but as the wavelength is increased, the absorption is also increased, and this absorption become maximum at wavelength 217 nanometer. So this is our lambda max. So the wavelength at which absorption become maximum is called lambda max. Now the other characteristic feature of this UV visible spectrum is, in UV visible spectrum the peaks are not sharp, but these peaks are broad. Now broad means this, you can easily see this peak is a very broad peak. Here it is like this, it is not a sharp peak, or it's not a line peak like this. So why is this so? This is not a line peak, but this is a sharp peak. So in UV visible spectrum these peaks, they are sharp peaks. Now this can be explained, as we have already discussed, in UV visible spectrum the electronic transitions take place. That means electrons from the lower electronic energy level jumps to the higher electronic energy level in the presence of UV visible radiations. And suppose these two are the two electronic energy levels. Suppose this is ground electronic energy level and this is excited electronic energy level. So the electron jump from this ground electronic energy level to this higher electronic energy level. But what happens, since these two electronic energy levels, they have a maximum energy gap, so each electronic energy level further consists of vibrational energy level. So it consists of vibrational energy level, and each vibrational energy level further consists of rotational energy levels in between them. Okay, so this whole is electronic energy level, then these are your vibrational energy level which are present in electronic energy level, and these are rotational energy level which are present in between vibrational energy level. So what I mean to say, each electronic energy level further has vibrational energy level and rotational energy level. So each electronic energy level also consists of vibrational and rotational energy level. Similarly, in excited state, each electronic energy state has vibrational and rotational energy level. So here in this case, this intermixing of transitions take place. Now that means when transition take place from the one electronic energy level to another electronic energy level, it also affects the vibrational and the rotational energy state. So the electronic transition can take place from the lowest vibration energy state to the higher rotational energy state, or from the another vibration energy state to the another rotational energy state, or it can take place from the one rotational energy state to the another rotational energy state. So there's an intermixing of these vibrational and the rotational energy states in electronic energy states. So all kind of these transitions take place. So due to this intermixing of transitions, it gives a large number of lines or the energies which are very closely separated. And due to this large number of lines which are very closely separated, it appears as a band structure, not as a sharp peak. So we can say, due to the intermixing of these vibrational and rotational energy states with electronic energy states, there is a large number of possible transitions take place, and these transitions, they only differ in slightly in energy, and due to which this results in absorption of large number of wavelengths which are very close to each other. So this results in absorption of large number of wavelengths that are very close to each other. So as a result, absorption spectrum consists of large number of lines which are very close together, and they appear as a band structure rather than the line structure. The next are the absorption laws. Now these absorption of these UV visible radiations are governed by a few laws that are called absorption laws. The very first absorption law is a Beer's law. Now, what Beer's law states that now when the beam of monochromatic light is passed, monochromatic means that consists of single wavelength, only one wavelength is passed through the substance which is dispersed in a non-absorbing solvent or which is dissolved in a non-absorbing solvent, the absorption of light is directly proportional to the concentration of that absorbing substance. So this simply means the absorbance of light depends upon the concentration of absorbing substance. Okay, so here suppose if A is your absorbance, or you can say if this is your cell, and if you have here your compound or anything which is dissolved in some solvent, and if you incident I naught is incident light and I is outgoing light, then this absorbance is directly proportional to concentration of this absorbing substance. Now more the concentration, more will be absorbance. So your absorbance which is also given as a logarithm of I naught upon I, where I naught is a incident light, I is a outgoing light, is directly proportional to concentration of absorbing substance. So this law is called Beer's law. Okay, then we have a Lambert's law. Now Lambert's law states that okay, again, when beam of monochromatic light is passed through a substance which is dispersed in non-absorbing solvent, the absorption of light is directly proportional to path length of sample of the substance. So what this means, suppose if you have these two sample, one is this sample and another is this sample. Now in both cases, now here the path length of sample is this one, say it's L prime, and here it is L. Now this law says that when the beam of light pass through the substance which is present non-absorbing solvent, then the amount of light which is absorbed depends upon its path length. So here its path length is more, that means here the absorption will be more. Here path length is less, here absorbance will be less. So it is directly proportional to path length of light, path length of this of the sample in substance. More the path length of the sample of the substance, more will be absorbance. The combination of these two laws is called Beer-Lambert's law. So what Beer-Lambert law states that Beer's law says that absorbance is directly proportional to concentration. Lambert's law states that absorbance is directly proportional to path length of the sample. So Beer-Lambert's law states that the absorbance is directly proportional to the product of path length of the sample as well as concentration. So both are directly proportional to each other. Okay, so here in this figure you can easily see the if I naught is incident light, I is outlight light, then absorbance is directly proportional to concentration and path length. More the path length, more will be absorbance. More will the concentration of substance, more will be absorbance. So if you remove the sign of proportionality here, it can be replaced by this constant epsilon, which is a absorptive constant or also called molar extinction coefficient. So A is equal to log I naught upon I is equal to epsilon LC, where epsilon is a constant called molar absorptive constant or molar extinction coefficient. While I is the intensity of transmitted light, I naught is intensity of incident light, C is a concentration of absorbing substance, and L is a path length of the sample, and it usually represent in terms of centimeter. If we want to calculate the units of this epsilon, so this epsilon will become absorbance divided by L into C. Now here, since absorbance is a unitless quantity, so it will become 1. The units of L are centimeter, length is centimeter, and units of concentrations are mole per liter, so it become mole per liter. Now, liter can be expressed in the terms of centimeter cube. So it will become per centimeter cube. So this will cancel out. It will become centimeter square. And when you invert it, it will become centimeter square per mole. So the units of this epsilon or absorptive constants are centimeter square per mole. Moreover, this epsilon or the absorptive constant can also be used to determine whether absorbance is very strong or absorbance is weak. If this value of epsilon or the constant is more than 10 raised to power 6, then it will be called very high absorbance. And if it is less than 10 raised to power 4, then it will be called weak absorbance. Okay, there are certain limitations of this Beer-Lambert's law. The very first limitation is Beer-Lambert law is applicable only when there is a single species are present. That means when in the solution form only one structural form is present. For example, it is not applicable when there is a keto-enol tautomerism is present in the solution form, because in that case there will be two structures and this law is not longer applicable. The second thing is this law is not applicable if there is an interaction between solute and solvent. Now, if solute and solvent interact with each other to form a complexes, in that case also this law is not over applicable. So this was the Lambert-Beer's law. So the learning outcomes of this lecture is, in this lecture we have learned what is spectroscopy. So what was the spectroscopy? Is a simple study of interaction of electromagnetic radiations with matter. Then we have seen different kind of electromagnetic radiations in the form of electromagnetic spectrum, and we have learned the various terms to characterize them. Then we have discussed principle of UV visible spectroscopy. So in UV visible spectroscopy, electronic transitions are involved in which electrons jump from the lower electronic energy level to higher electronic energy level. And we have seen the presentation of UV visible spectrum, in which the UV visible spectrum is drawn by taking absorbance on the y-axis while wavelength on the x-axis. Then we have discussed Beer-Lambert's law and its application limitations. Thank you very much.